Hello guys, welcome back to my channel. And today I have a weird infinite series for you. So let's get to it. So now they want us to calculate the sum from n equals 0 to infinity of the square root of 2 minus 1, the whole thing raised to 2n plus 1 power divided by 2n plus 1, the whole thing squared. So I just want you to notice that this square root of 2 minus 1 is a relatively arbitrary value because it does not depend on n. So, instead of uh, having an arbitrary value inside, let's define a general function, call it f of x, which is defined as the sum from n equals 0 to infinity of, instead of this square root of 2 minus 1, we can have x to the 2n plus 1th power divided by 2n plus 1, the whole thing squared. And just to give you an idea of what this f of x looks like, when n is 0 we have 1, same thing here, so x to the first power over 1, which is squared, plus there's no alternating part, so we have less to worry about honestly. Then when n is 1, 2 times 1 is 2 plus 1 is 3, so x cubed over 3 squared. And then when n is 2 we have x to the 5th over 5 squared. So in other words, it's a sum of x to an odd integer over that odd integer squared, right? And this basically goes on till infinity. Now what can we do here? Looking at the form of this thing, we might want to refer to our table of Taylor series. And when we do that, the closest series, the closest Taylor approximation for a function that is closest to this question that we had, f of x, is the hyperbolic inverse tangent of x, because that's x plus x cubed over 3 plus x to the 5 over 5 plus x to the 7th over 7 plus till infinity basically. Now we might want to condensify this by letting the sum from n equals 0 to infinity of x to the 2n plus 1 power over 2n plus 1. Well, great, right? I mean, we have the exponent of the x that fits well with our original question, but only problem is we have a square in the denominator, and here we don't. So we have to do some operation on this Taylor series of the inverse hyperbolic tangent so that we obtain our a denominator squared. Some operation, I'm thinking of integration, because that's a convenient method, I think, of doing something like this. So first let's just rewrite our f of x. So what's f of x? F of x is basically the sum from n equals 0 to infinity of well, we have x raised to 2n plus 1 over 2n plus 1, the whole thing squared, right? Now you can just rewrite this thing in terms of an integral, because okay, say we bring one of this out, so 2n plus 1 outside. Why don't we set an indefinite integral of x raised to 2n dx? Because what that will do is, say if you apply the power rule of integration, you will have a power plus 1, right? So you'll have a 2n plus 1, x raised to 2n plus 1 divided by a 2n plus 1, right? Divided by the new power. So when you evaluate this indefinitely, you'll have this expression, and then when it gets multiplied by this 2n plus 1 that's already outside, you'll just have x raised to 2n plus 1 divided by 2n plus 1 the whole thing squared, which is indeed our f of x. So we can definitely write this way. I hope you understood. Okay, let me just explain it again. So we had our f of x this way, right? So we had to relate f of x to this hyperbolic inverse tangent in some way. So we had to relate this single denominator to a denominator squared. So one thing where we could do is we could indefinitely integrate x to the 2nth power, because then you will have to apply the power rule, and by the power rule you have to increase the exponent by 1 and divide it by the new exponent. So uh, if we integrate x to the 2nth power indefinitely, you end up with this expression. And since I put a 2n plus 1 outside, 1 over 2n plus 1 outside, ultimately I'll have x raised to 2n plus 1 upon 2n plus 1 the whole thing squared, which is indeed our f of x. So this equality definitely holds. Now why don't we write our x raised to 2n in a special way? By special I mean something that in essence looks like this thing. So we can write this as x raised to 2n plus 1 divided by x. So it's essentially multiplying and dividing by x. Now we can interchange our limit and sum. So sorry, our integral and sum. So we can take the integral outside, and all the things that do not depend on n can be taken outside. So this 1 over x can definitely come outside, and we have the sum for n equals 0 to infinity of x raised to 2n plus 1 upon 2n plus 1, and don't forget the dx. Now what does this thing look like? That's right, we just defined it at the start of the video. That's the Taylor series for the inverse hyperbolic tangent of x. Inverse tangent of x. Precisely. So our question now becomes 1 over x, and then this whole thing I can substitute for inverse tangent of x. Don't forget the dx. And what was this? What were we equating this to from the start? That's right, f of x. So look at that. We just simplified our infinite sum into an indefinite integral. So f of x is nothing but inverse tangent of x divided by x, and that's an indefinite integral of that. So we obtained that our f of x, our general series from n equals 0 to infinity of x to the 2n plus 1th power over 2n plus 1 the whole thing squared, is nothing but the indefinite integral of tangent inverse of x divided by x, integrated with respect to x, obviously. Well, we just simplified our question a whole lot. And if you remember my last video, we had exactly calculated this using we'd calculated this indefinite integral using a new definition for the inverse tangent of x. So we had obtained like a natural log of 1 plus x on one side and natural log of 1 minus x on one side. Then we used some Taylor series, and then we got a definition for the dilogarithm function. So I'll just write the answer for now directly. So this is half times the dilogarithm of x minus 1 half the dilogarithm of negative x, and don't forget the plus c, the constant of integration, because let me remind you, this is an indefinite integral, right? I mean, there are no upper and lower limits over here. There's no upper and lower bound here. So we can't forget this plus c. Okay, fine. This is our f of x, right? Finally. But our original series was the f of square root of 2 minus 1. And even if we plug square root of 2 minus 1 instead of x, we'll always be left with this c, right? So how do you get rid of this c? Well, you can get rid of this c by basically substituting x as 0 in an ideal case. And even now, because when you do that, well, when f of 0, so when you take 0 to the 2n plus 1 over 2n plus 1, the whole thing squared, this thing will go to 0. And the dilogarithm of 0 is 0, and the dilogarithm of 0 again is 0. So 0 will equal 0 minus 0 plus c, so c will be 0. Let me just show that, probably give you more mathematical insights into why the dilogarithm is 0. So wait, f of x is nothing but the sum from n equals 1 to infinity x to the 2nth plus 1 power divided by 2n plus 1, the whole thing squared, is equal to half of the dilogarithm of x minus half of the dilogarithm of negative x plus c. So f of 0, well, 0 in the numerator will make this thing 0, is equal to, well, what's the definition of the dilogarithm? Say you have a sum running from n equals 1 to infinity, and you have some x that's being raised to the nth power like a polynomial, and you have, since the base is 2, right, it's a dilogarithm, you have a 2 in the base, so n squared. And you can similarly define, call this m now, 1 to infinity of negative x to the nth power, sorry, mth power, because now we defined it as m, divided by m squared because the base is 2, right, plus c. Well, now instead of this x, f of 0, right, so instead of x we can plug in this 0. Same thing here, because by virtue of the 0, this thing goes away to 0, this thing goes away to 0, and basically you're left with c is equal to 0. So finally, we don't even need to write the c. That's what this thing is telling us. So f of x is nothing but half of the dilogarithm of x minus half of the dilogarithm of negative x, and we don't even need to write plus c because c is just 0. Well, what was our original question? As I said, it was the f of square root of 2 minus 1. So instead of this x, we can definitely plug in square root of 2 minus 1, and the negative x will make it 1 minus the square root of 2. Now the question is, how do we simplify this further? Now let's simplify this on another page. Well, we know an interesting identity of these dilogarithm functions. So we have the dilogarithm of, say, 2x minus x squared, that's equal to the negative natural log square of 2 minus x plus pi squared by 6 minus 2 times the dilogarithm of 1 over 2 minus x plus 2 times the dilogarithm of x. So basically we have to make a wise choice for x. The best choice we can make is let x equal 1 minus square root of 2. So this side we'll have the dilogarithm of 2 times x, so 2 minus 2 root 2, and then x squared, so 1 negative 1 because of that, plus 2 root 2 minus 2 because it's root 2 squared, right, and a negative on that, is equal to minus ln squared of 2 minus 1 plus root 2 plus pi squared by 6 as it is minus 2 times the dilogarithm of 1 over 2 minus 1 plus root 2 plus 2 times the dilogarithm of 1 minus square root of 2. Now look at this argument here. This is definitely cancelling out. This 2 and negative 2, and in the end we are left with the dilogarithm of negative 1 is equal to minus a natural log squared of 1 plus square root of 2 plus pi squared by 6 minus 2 times the dilogarithm of 1 over 1 plus root 2 plus 2 times the dilogarithm 1 minus root 2. Well, everything else is simplified. Now we only need to simplify this. We need to only rationalize the argument of this dilogarithm. Well, let me remind you what the value of dilogarithm of negative 1 is. It's basically negative pi squared by 12 because it just relates this. A negative dilogarithm directly relates to the Dirichlet eta function. I could probably show you in like another video if you want, but I think it's pretty obvious. Minus ln squared of 1 plus square root of 2 plus pi squared by 6 minus 2 times the dilogarithm, and then we can multiply and divide by the conjugate of this 1 plus square root of 2 times 1 minus the square root of 2 plus 2 times the dilogarithm of 1 minus the square root of 2. So we have negative pi squared by 12 equals negative ln squared of 1 plus square root of 2 plus pi squared by 6 minus 2 times the dilogarithm of 1 minus square root of 2 divided by, we can use a plus b into a minus b, which equals a squared minus b squared, the difference of squares formula. So 1 minus root 2 squared, 1 minus 2 is a negative 1 now, isn't it? Plus 2 times the dilogarithm of 1 minus square root of 2. This finally evaluates to negative pi squared by 12 is equal to minus ln squared of 1 plus square root of 2 plus pi squared by 6 minus 2 times the dilogarithm of root 2 minus 1 plus 2 times the dilogarithm of 1 minus root 2. Now why don't we make these two terms the subject of our equation, because if you remember what we originally wanted to find. So when we do that, we obtain 2 times, well, that we can take common, the dilogarithm of square root of 2 minus 1 plus the dilogarithm of 1 minus square root of 2 is equal to pi squared by 4 minus the natural log squared of 1 plus square root of 2. But we want half of that, right, according to our original question. So we can divide by 4 on both sides. We can divide by 4 like this. So on simplification, we obtain half of the dilogarithm of square root of 2 minus 1. I'm so sorry, this is a negative here. My bad. Minus half of the dilogarithm of 1 minus square root of 2 is equal to, where 4 times 4 is 16, so pi squared by 16 minus natural log squared of 1 plus square root of 2 all divided by 4. And all this I can, just for the sake of completion, say that this is the infinite series as n equals 0 to infinity of square root of 2 minus 1 to the 2n plus 1th power divided by 2n plus 1, the whole thing squared. So, it's a pretty neat result. I mean, it was quite unexpected to see the dilogarithm or Spence's function in this way. So I hope you enjoyed this video. Please like, share and subscribe. If you have any doubts, please use the comment section to reach me. And that's it for today. Have a great day, guys. Stay home, stay safe. Peace out.